So using this idea, so we're getting started for the second hour of Physics 1C here. So the idea is that if you've got a piece of wire and you place it into a magnetic field, then that piece of wire is going to experience a force. And so, one thing we could do is say, well, what if I construct a loop of wire like this? Okay. We construct a loop of wire like this, and we place it into a uniform magnetic field. Now, in this picture, it seems as though the magnetic field stops on the left-hand side, but the idea here is, the magnetic field actually goes straight through. So the whole thing is in a magnetic field that points like this, okay? And now we think about the direction of the forces on each of these pieces of wire right here, okay? So let's think about each piece. So if we look at the side 1 right here, can you guys tell me, based on our rule, what's the direction of the force, or is there no force, on the top wire segment right here? You guys understand the question? What's the force on this top wire right here? Your waistline is growing sideways these days. Me too. Jesus Christ. Not being able to go to work, one of the main ways I get exercise is just by standing in front of the classroom and walking around. Anyway, so yeah, what's the direction on no force on the one on the top and on the bottom? That's right. When you have a wire that has a current running parallel to the magnetic field, then we can say the force, I don't want to use that color, we'll use this one. We could say the force on wire 1 is going to be equal to 0. The force on wire 3 is going to be equal to 0, right? What about the force on wire 4? What direction is that going to point? In this picture here, what's the direction of the force on this one going to be? Is it into the page or out of the page? The force on wire 4, is it into the page or is it out of the page? Scroll down. In? Yeah, see, I cross B, yeah, into the page, right? And then on this one, it would be out of the page then, right? So what that means is if the force on 4 goes in, and we can draw that here like this, right? That's the direction of the force on this one. And the force on the other side comes out. Then you could imagine, well, if I took an axis, right? Like, let's say I cut a hole in the bottom of this side right here, and I just cut my object in half with an axis, okay? And we make it so that we can rotate our system around this axis. And then we look at it from a different viewpoint, right? We hinge it at point O. We say that this is side 4. Let me make this picture just a little bit bigger here so you can see some of the details of it. So we hinge the object at point O. Okay, so this becomes a axis of rotation. So it's free to rotate about that point, right? And then what happens is that you have the force on this side going down, the force on that side going up, and that means the object is going to kind of rotate, right? It's going to create a torque that tends to rotate the loop clockwise. So hopefully that all makes sense to everyone. Because then what we can do is we can say, well, what's the magnitude of this torque, right? So to find the torque, we need to know what the values of F2 and F4 are. So F2 is, which side is 2? This side is 2 over here. The dimensions of our object are A and B. Okay, so one side is A and one side is B. So the force on the left-hand side should be equal to the current that flows there, which is I, multiplied by the length of the wire, which is A, and then multiplied by the size of the magnetic field, which we're just calling B. Likewise, the force on object 4 is going to be exactly the same. It's also going to be current multiplied by the length multiplied by the size of the magnetic field. And now what we're really looking for is torque, right? So to find the torque about this point, right, we would say that if we define clockwise to be positive, so CW is clockwise for torque, then we can say that the torque due to wire 2 plus the torque due to wire 4 should be equal to, they're both going to be clockwise torques, and to find torque you need to take the force, like F2, and you need to multiply by the distance to the axis, right? Which in this case is going to be times B over 2. And then we'd also add to that the force from 4 multiplied by the lever arm there, which is going to be also b over 2. So the total torque, this is going to be the net torque, you might say, is going to be F2, which is IAB, times b over 2, plus also F4 is also IAB, times b over 2. So the net torque that we get here is going to be equal to just I times A times little b times big B. Now, if we look at the answer that we get right there, notice that the area shows up in here. I was going to ask you guys what A times B represents, and I didn't do it. But in this case, A times B happens to be equal to the area of the loop, right? One side is B, one side is A. The area is A times B, right? So another way to write this would be to say that the torque is actually equal to I times the area of the loop multiplied by B. And I'm going to tell you now that this is actually the maximum torque that the system is going to experience. I times A times B. I say it's the maximum torque because if we think about what happens when our system rotates a little bit, so if we think about what happens when, oh man, I really don't want to try to draw this. There's too many things, and it will take quite a while. So I'll try to find the figure that goes with this. I left it out. Does page up let me go one at a time? Kind of. Where is the picture of the next part? Because after it rotates, here, this is what I want. That picture right there. Will it copy paste for me? Nope, it doesn't like that. You know what? We're going to copy both of these things because I want both of these pictures, actually. Sorry, I don't want to try to draw this picture. I could try and it might be actually more instructive, but I don't think I could get all the details in as well as this picture has here. So if we imagine what happens to our loop here, I'll leave both of them on the screen, after some time has passed, it's going to rotate, right? And it's rotating about this hinge O right here, or this axis O right here. And at some point in time, that axis O is going to create, kind of an angle. And in this picture, what they've done is they've chosen to define what's called an area vector that points like this, okay? If you look at the way that the current is moving, this picture right here will show you how that area vector was defined, right? You curl your fingers in the direction of the current. So if the current's flowing around like this, you curl your fingers in that direction, and it tells you the direction for the area vector associated with the loop, okay? So that's the area vector A. So after the object has rotated a little bit, that area vector is going to make an angle theta relative to the magnetic field. Remember, the magnetic field was pointing to the right, like here. So now at some point, after it rotates a little bit, there's going to be an angle. I should say one thing here. On this picture, the area vector would be pointing like this, right? So what's the angle initially? What's the angle theta to begin with? This would be theta here, right? It starts off as equal to what? 90 degrees, yeah? And it's going to get smaller, okay? Now, in order to find what the torque is in this case, now the torque is going to be equal to, we need to find the torque due to like force F2, and I would say that it would be equal to this. It's going to be equal to F2 multiplied by B over 2. That also showed up right here, right? That was the distance. But now we also need to multiply this by sine theta, okay? And if we do that, I don't know if you guys remember this. This distance here is called the lever arm. When you take a force and you just basically drop a line down, and then you drop a perpendicular like this over to the axis, then this distance here, which is b over 2 times the sine of theta, is what we call the lever arm, and the torque due to the force is equal to the force times the lever arm. Do you guys remember that? Torque is equal to force multiplied by the lever arm. And can you identify that this is the lever arm here? Does that make sense to everybody? Does that look familiar to you? Okay, so it's been a long time, I'm sure. So the total torque now, right, is going to be equal to F2 times B over 2 sine theta plus F4, and then F4 is going to have the same thing. And maybe we can draw it on here. Here's what you do. You take a line, and you basically just extend it up and down forever. To find the torque, you need to find the shortest perpendicular distance to that line, which is this distance right here. And you can easily see that this is theta as well, so that since this side right here is B over 2, that this side here has to be equal to B over 2 times the sine of theta. And that is the lever arm. So the torque for F4 is going to be, so F4 times B over 2 sine theta. Putting these together, what we end up getting is I, A, B, B sine theta. Or just I times the area times B times the sine of the angle theta. That ends up being equal to the net torque in this situation. Now this torque is always going to be smaller than what I call the maximum torque right here, right? Because it's reduced by this sine of theta right here. Now there's another way we can write this. Another way we could write this is to say this is actually the same thing as saying that the torque is equal to the current multiplied by the area vector for your system cross product with the magnetic field. That's basically what that expression right there says. It's IAB sine theta, and the direction of the torque is in the direction of A cross B. I don't know if you can see that here, but in this picture, your magnetic field vector points this way, right? So you guys tell me, if you do A cross B, what's the direction of the torque? If you do A cross B, use your right hand, right? So you point your fingers of your hand to A, you rotate them to B. What direction is your thumb pointing? Into the screen. And that would be kind of a clockwise rotation. Would you agree? Would you guys agree it's a clockwise rotation? Your hands go from A to B. That's clockwise, right? So, yeah, I hope you see then that this is an expression in general that gives you what the torque is. Okay? Now, we're going to extend this even further, and we're going to say, and we'll do problems with this stuff, okay? So if you don't understand yet, I hope you'll understand a little bit more when we look at problems. What we're going to do is we're going to say, let's define a new quantity, okay? So let's let the symbol mu, okay, be defined as the current flowing in a loop of wire multiplied by the area of the wire, okay? You take the current and you multiply by the area. Now, we derived this for rectangles, but this expression, it also works for circles too. It works for any shape of wire, okay? So it works for coils as well, and that's actually normally what we're going to have. So the area here could be the area of a circle, it could be the area of a square, anything like that. But then we define this quantity here, I times A, to be mu, and then we can define the torque in a more general sense as simply being this quantity mu crossed with the magnetic field B, okay? And you can see from this picture right here that that direction of the mu vector, which is this vector right here, is pointing in the same direction as the area vector, right? This ends up being our general expression, but we also need to define this here. And we call this magnetic, this is a great name, magnetic dipole moment. The magnetic dipole moment. Now, what this thing does, okay, is it tells you the way that your loop of wire responds to external magnetic fields, okay? It tells you the way that your wire responds to external magnetic fields, okay? So let me make some space here. Just come way down here. So I give you a loop of wire, okay? And this is my loop of wire. And we say that there's current flowing like this and like this, right? It's coming kind of, this is the front and this is the back over here, right? And now I say that this loop of wire has a magnetic moment vector that's going to point like this, right? You curl your fingers in the direction of the loop, right? Now, suppose that I place this entire system into a magnetic field, okay? And let's say that my magnetic field vector points like this. Not due to the wire, but there's just some external magnetic field. So, what is this thing going to do? Well, it's going to experience a torque that's equal to mu cross B. Now, what that really means is that eventually this torque is going to have the effect of rotating the mu vector down to B. Does that make sense to you guys? So, after some time, mu will point parallel to B. At some point in time, mu is going to point in the same direction as magnetic field. Does that make sense? At that time, what's the torque going to be equal to? What happens to the torque when they are parallel to each other? It's zero exactly. So effectively what will happen after some time is that our loop of wire right here is eventually going to be oriented kind of like this, right? With its current flowing this way, and this is a horrible picture, but the current's kind of going like this. The magnetic moment vector, or the magnetic dipole moment vector, is going to point like that, and it's going to be exactly parallel to the magnetic field vectors. And at this point, there's no more torque, right? So effectively, the coil is just going to line up with the field. Does that make sense? The coil is just going to rotate. You can literally think about this magnetic thing. You can compare this to a compass. Okay, so if I have a magnetic field, like let's say there's a magnetic field, take a really simple one like this, and I come in here and I place a compass in here, and I set my compass up like this, okay, and I tell you that this side is the north side, right, and that this side is the south side, so this is the north end of my compass and this is the south end of my compass. What's that compass going to do? It's going to rotate, right? It's going to rotate until the compass lines up exactly parallel to the field. I mean, that's how a compass works after all, right? You guys understand? You guys get what I'm saying here? Like, the coil, it acts just like a compass would, in the sense that it's going to eventually point so that it's parallel to the magnetic field. Parallel to the magnetic field. That's what the magnetic moment vector does, is it tells you exactly how these objects line up with external magnetic fields. And I wonder if I can find something here for you about... you can... I need to set this up more. There's something else I want to look up. I don't want to do it on the fly because it didn't immediately find what I wanted to find. Yeah. Anyway, so this is magnetic dipole moment. Okay, it's a new concept that we're learning here, and it is pretty handy for solving some of these problems. Okay, it's just equal to current multiplied by area, and the torque on a loop of wire is equal to that vector crossed with the magnetic field vector. It has the effect that when you place a loop of wire in a magnetic field, if it's free to rotate, that loop of wire is going to tend to align with the external magnetic field. All right. So we're going to use this concept to solve a couple problems here. Not this one. I think we're going to use it. I had another one I thought that was easier than that one, but I guess that's the only one I put up here. Maybe I decided the other one was a little too trivial. All right, we're going to do this problem here. Let me just make sure I don't have another problem sitting around here that I wanted to do. Nope, I think that's just that one there. Okay. So put this here. And I'll put the equations back up here as well. This is going to be one where I definitely want you guys to try to solve this a little bit yourself. Oh no. So our equations were that magnetic moment is equal to current multiplied by area, and the other piece is that the torque on the loop ends up being equal to the magnetic moment crossed with the magnetic field. Those are the two equations that we have. Okay. I is current. Do I need to label what these things are in case there's any confusion? So I is obviously current. A is the area of the loop. And E's magnetic field. We've been using that a lot, so that should be clear. And then tau is torque. So we have a rectangular loop. I'll make this a little bit bigger. I don't know what kind of screens you guys are on here. The rectangular loop is pivoted about the y-axis, so it's pivoted along this axis right here. You were stuck on the homework with finding torque. You're going to try it out after this class. Yeah, okay. Hopefully after today you'll understand a little bit how to do this. It's definitely like a little bit tricky to understand, but it's not as hard as you might think. It requires some three-dimensional like spatial thinking. You need to be able to visualize these things, but ultimately the calculations aren't that hard once you figure out the directions. So rectangular loop is pivoted about the y-axis. It carries a current of 15 amps in the direction as indicated. So there's the direction of the current. If the loop is in a uniform magnetic field with a magnitude of 0.48 Tesla in the positive x direction, so there we know what the magnitude of the magnetic field is, right? Oh, why doesn't it let me pick this? Oh, maybe it will. No, what's it doing? Whatever. So the field, B, is equal to 0.48 Tesla multiplied by I hat. So it's a uniform field. Find the magnitude and direction of the torque required to hold the loop in the position shown. Okay. So I want you guys to think about this and try to solve it. I'll give you like 5 to 10 minutes, depending on like how long you might need. But I'm also going to tell you, in order to make this process a little bit quicker for you, that it's a little easier to think about this if we draw kind of a sideways picture. Okay, so what I'm going to do is let's make it so that this is the x. Oh, we can use the axes for this probably. They're probably not going to point in the way I want them to point though. Let's see. Maybe this one will work. Yeah, and then I can just like erase part of it or something. I think it'll let me erase part of this, right? Yep. Okay, let's erase this piece. Let's erase this piece. And then we'll grab this guy. We'll move him up this way. So I want to reorient this like this. I'm going to say this is my x direction. That's my x direction. This is my z direction. And then positive y will be coming out this way. So this is the y direction. Coming out, so I put that little dot right there. That's positive y. That's positive z. And that's positive x. So now my loop, right, is basically oriented at 30 degrees, like right here. And the direction of the current in the loop is such that the current here is going into the page, right? That's this one, in. And the current on the other side is going out of the page. So the current here, this is going to be kind of, the current is also coming out of the page here. So basically the current is flowing along the positive y-axis. Can you guys tell me what is the direction of the magnetic moment for this loop in my picture right here? Now, what is the direction of mu? All you need to do for this is to just curl your fingers in the direction that the current's rotating. Maybe it's easier for you to do on this picture. I don't know. But it's always going to point perpendicular to the area of the loop, right? It's perpendicular to the area of the loop, right? And you just rotate your fingers in the direction the current's flowing. So basically, it's either going to point this way or it's going to point this way. Is it the top one or the bottom one? Which one of those represents your mu vector? It's the top one. Yep. This is the direction of mu. Convince yourself that that's true. All right. And then see if you can figure it out. Yeah, try to solve, just try to solve part A only, and we'll do the other two parts. If you can get part A, the other two are really easy. And what's, yeah, magnetic field. I guess I could draw the magnetic field on here too, couldn't I? This is the direction of the magnetic field. B points this way. What way is it going to want to rotate? It's going to rotate until what happens between the vectors mu and b? Yeah. Now our goal here is to figure out what torque we need to stop that from happening, right? But whatever the torque is that this object is feeling from the magnetic field, we just need to have exactly the opposite torque, right? So, all right, see if you can't calculate it. And we'll talk about it here in a second. So I'll give you guys 5 minutes to think through. This is what I want. I just misspelled it when I typed it into Google. But what I was going to say is that any object that has charges that rotate have magnetic moments. Even nuclei of atoms have magnetic moments, okay? And, yeah, so, like, this is hydrogen. I think this is deuterium. This is lithium, carbon. Right, this is, if the mass is 2, it's deuterium, right? Yeah, deuterium. Okay. So that's just a hydrogen atom that has one extra, wait, what? What is it? Do you guys know? I know what it is, but do you guys? What's the, what extra neutron, right? It's an isotope, right? So these are their magnetic moments right here. I didn't mean to do that. Magnetic dipole moment. So even a single atom has a magnetic dipole moment. So for hydrogen, it's 2.79. It's using a unit called the nuclear magneton. You can see what it's equal to right there. It's equal to E times h bar, which is Planck's constant, divided by 2 times the mass of the proton. But yeah, every one of these things has a magnetic moment. You know what that means? That means that if you put a bunch of hydrogen into a magnetic field, what's going to happen to the hydrogen molecules? What's a hydrogen molecule? We can take the simplest, almost erroneous version of what a hydrogen molecule is, and we can say a hydrogen molecule is basically like a single proton that has an electron that's orbiting it, right? With some velocity v. So we've got our little electron that's going around in a circle right here, this negative charge. And that negatively charged electron moving around in a circle like that is effectively the same thing as a current that's flowing in the opposite direction, right? So what would the direction of the magnetic moment for this object be? It would point straight down. The magnetic moment for this object would be pointing this way, right? So now imagine that you place such an object into a field, you know, maybe that you put it into a magnetic field that points like this, then the hydrogen atoms are going to basically, they're going to rotate like that until they line up with the field, right? Everything has a magnetic moment, and you can exploit that for various reasons, for magnetic levitation, all these kind of things, but even the motion of these charges and the spins of their nuclei and stuff like that have an effect on this thing called magnetic moment. Okay. Sorry, I didn't mean to interrupt, but I just wanted to show you guys that as well. Okay, I'll give you guys a couple minutes more to figure this out. Do you get an answer yet? .03. Okay. Anybody else? I'm assuming NM is Newton meters, not nanometers. Why is your name IFBB Pro Coach Greg Doucette? What does that mean? Memes. What is IFBB? He's a YouTuber? Oh, okay. Cool. What's IFBB stand for? If you don't want to say, you don't have to. I assume if you made it your name, you don't mind talking about it then. International Fed of Bodybuilding. Okay. I see that's why you've got the bodybuilding image as your profile there. Nice. It's a troll for John. Well, right on. John Coronius, or John is in someone else in the class? Yeah, John in class. Right on. Okay, let's talk about how to solve this. So you've got our area vector here, which I think I calculated correctly. You get that by just doing 6 times 8. The direction of the area vector is the same as mu, and we can calculate what mu is equal to. Okay, mu is just equal to the current multiplied by the area, and that doesn't have the direction associated with it, right? So really what we would be doing here is the magnitude. So if I want to find the torque, I would just take I times A cross B. To do this, we need the current, which is 50 amps. We multiply that times the area vector. I think I did this calculation right, but you guys tell me if that's right or wrong. 0.0048 meters squared. We do need to have everything in SI units. We're crossing this with B, which means you can multiply by the size of the magnetic field, which is 0.48. And then you just have to multiply by the sine of the angle between the magnetic field vector and between the magnetic field and the magnetic moment. And what I would say in this case is that since the magnetic moment vector makes a right angle here, that's a right angle, then I would argue that this angle here should be 60 degrees because theta was 30 degrees, which means that this angle here is also 60 degrees. So the angle between the two of them is 60, so we do times the sine of 60, and that should give us our answer. So that's 50 times 0.0048, also times 0.48 Tesla, and then times sine 60, which is root 3 over 2. So we'll just put degrees, sine 60, close parentheses. Oh, so I got 0.1. It was different from what someone else got. I wonder if I did something wrong. So I got 0.1. Is that what it was? Yep. It's 15. Did I make a mistake? Oh, it is 15 amps. Oops, I'm sorry about that. Thank you for noticing that. We'll put it in red since I made a mistake. So this is 50. And... Oh. Sorry. 15. So this should have been 15. So to get the correct answer, we can just basically divide by 50 and multiply by 15. Yeah, 0.03, that's what you guys got. Good. Now, the other thing about this is that technically, if we want to write this as a vector, we're going to need to put a symbol in here. And I would argue that the direction of our torque, since it tends to rotate mu from here to here, right? This object is basically going to swing like this. then I would define that torque to be times negative j hat, because it points along the, it points along, it's a type of rotation that points into the board. It's not super important to think about it that way if you don't want to, but that's the torque that's needed, that's coming from the magnetic field. The opposite torque that we need in order to hold the wire in place would just be the same torque times j hat. Just the same torque, but pointing in the opposite direction. Okay. So does this make sense to you guys? Does anyone have any questions? One other thing I want to mention here in case you have a question. The negative j, what that means. Yeah, this is just about the way that rotation works. So, like, it wants to rotate this way, right? That's the way it's going to rotate, right? And the way we describe that type of rotation, if we want to make a vector for it, yeah, is we say that it's the type of rotation that it's like you point your thumb. I wish I could show you. You point your thumb in the direction of the y-axis, and the direction that your hands rotate is the direction of the torque, okay? So if you point your thumb along the negative y-axis, your fingers rotate in the direction that's called clockwise, right? So negative j hat in this case, actually, this just, all that means is clockwise, and all of this means is counterclockwise, okay? Because if you point your thumb in the direction of positive j, then, and that's just how we define these torques, basically. And it looks like you understand, so that's good. I want to mention one other thing here too, by the way. What's the direction of the force acting on this little piece right here? The piece that's here, this side. What's the direction of the force acting just on that little piece right there? Is it up or down? Magnetic field to the right, current going into the board. What's the direction of the force on this piece? Is it up or down? So this is a wire that carries current. It's represented by this one right here. Magnetic field to the right. What's the direction of the force on this one? Is it up or is it down? Yeah, it's down, right? I wish I could figure out how to draw straight lines like that every time. So, hopefully, if the way we talked about this didn't make sense, if you understand that this force goes down, then this object is going to tend to rotate this way, right? And to combat that, you need a force in the opposite direction here that is going to be equal and opposite to prevent it from moving. That's, after all, what we were trying to find. We were trying to find the magnitude and direction of the torque required to hold the loop in the position shown. And that's why this would be the answer, basically, here. Okay. Do you guys have any questions? What about part B? We might as well do these other ones. I'm not going to spend as much time on them. But part B says, repeat part A for the case in which the field is in the negative z direction. Okay? So negative z would be our field now. Okay? So now here's our axes, right? And negative z, this is kind of weird, but positive z is this way. Negative z is actually this way. It's up. So if our field was pointing in that direction, and our loop is just as it was before, so here's our loop. Might as well use blue again. So there's our loop. And our magnetic moment vector. And I'm going to actually draw the magnetic moment vector over here because it doesn't really matter where I draw the vector. So there's our magnetic moment vector. Now the size of the field is exactly the same. There's only one thing that's different now. The angle here is now 30 degrees, right? So now your torque is going to be equal to IA, this would be for part B, IAB times the sine of 30. That's really the only thing that's different here. It's just this angle. Also, the direction of rotation is going to be different because this thing's actually going to rotate that way. Again, the whole idea is that the magnetic moment tends to line up with the external field, right? So there's a torque problem. And I think you have more than one of these, but I think this covers most of what you're going to see on your homework, hopefully. All right. Should we talk about motors now? I left that out of the list. But we have everything we need now, effectively, to talk about motors. I don't know. It might be too much. I might want to kind of just move on to the new topic and talk about motors at a later date. I will say, if we go back and look at how we started this discussion, we said that if I have a system like this, and I've got current flowing through the system, that there's going to be a torque that's going to tend to cause the area vector to line up with the magnetic field. So the system is going to rotate in this clockwise direction here. And we said that that rotation would basically occur until the area vector and the magnetic field vector lined up, right? Now, if you're really clever about the way you hook up a system, then you can kind of make it so that the direction of the current swaps every time that happens. And if you do that, you can produce what's called a DC motor. And your book has a nice picture of this. Actually, not your book. Your book has a picture that's really hard to understand what's going on. But this other book does have a really good picture of how this works. Oh, is it not in this chapter? Or is it before this? Okay, I guess it is in your book that shows up. Let me pull this picture over here, because I feel like this is the right time to talk about motors now. What is a motor, by the way? Yeah, their picture's okay. We can work with this. We have a really nice, like, full-scale model of this at the school. Let's throw this in our document here. And I'll try to describe what's going on. Again, this is something where I could try to draw this using pen and paper. I don't even like drawing this on the board in a classroom. It's really hard to draw this picture. You kind of need, okay, we call this a DC motor. Okay, a motor, too many pictures. Yeah, I don't know what to say. I'm not trying to overwhelm you guys. I just, this kind of stuff, it's very difficult to draw three-dimensional images, especially with the a pen here. So we call this a DC motor, and I'll describe what this is. A motor is basically something that takes electrical energy and converts it into mechanical energy, okay? Okay, so here's what this thing says, and we'll kind of just read through this slowly so we understand what's going on. So schematic diagram of a simple DC motor. The rotor, okay, the rotor is the piece that rotates, right? Rotor for rotate, is a wire loop that's free to rotate about an axis. The rotor ends are attached to two curved conductors that form the commutator. Okay, this is an important piece of this. The rotor halves are colored red and blue for clarity, okay, but this is the thing that we call the commutator, and it has this feature that it's split. Sometimes it's referred to as a split ring commutator. So let's look at this picture about what's going on. You've got the north end of a magnet on one side and the south end of a magnet on the other side. That means that the magnetic field points to the right. That's this little blue line right here, right? Within this magnetic field, you put a loop of wire. And the loop of wire here is connected to a battery. So there's your battery, right? Current flows this way, up this way, into here, and then it continues along your loop. So your loop is this red and blue piece right here. I should indicate that with a pen probably, or the mouse so that people can see it on YouTube. This little red wire, that's where the positive current comes from. It comes in here, it flows around this way. Can you convince yourself that the magnetic moment is in the direction that they've shown by wrapping your fingers in the direction of the current here? If you roll your fingers in the direction of the current, you should find that your thumb points downwards. So convince yourself that that's true. So now, before we look at the next picture, can you guys tell me What direction would this system tend to rotate? Would it be clockwise or counterclockwise? Is this thing going to tend to rotate clockwise or counterclockwise? Mu is down, B is to the right. Yeah, counterclockwise. The mu is going to tend to rotate and swing up, right? Basically, the idea is you should think about it as the mu basically just tries to align itself with the magnetic field. Okay? Okay. I hope that you guys can at least kind of visualize what's happening here, right? So, like we said, as soon as the magnetic moment lines up, okay, if we didn't do anything else, the thing would stop moving, okay? But what happens in this case, if you notice these brushes right here, they make contacts, but there's this point where there's a split. So what happens is when those brushes line up with the place where there's a split, there's zero current on the wire, right? And what will happen then is because there's zero current, there will be no force holding it in place, and its inertia can allow it to continue to rotate in the same direction. And then what happens is the moment that the object kind of rotates past that point, then the current flowing through the wire actually swaps directions. It doesn't really swap directions. It basically just ensures that you repeat the same process so that you go from 1 to 2 to 3, and you might notice that picture 3 is identical to picture 1, so the whole system can basically come back around and repeat this process again. So they're aligned 90 degrees, 180 degrees, but you'll notice that now the current's flowing exactly the same as it was before. The only difference being that the blue wire is now where the red wire was, right? That's really the only difference between the first picture and the last picture, right? They're identical pictures if you look at them. Take a second and look at picture 1 and picture 3. They're 100% identical. It's just that the red and the blue have swapped places. Yet the wire doesn't know what color they are. That's absolutely right. It doesn't. That's right. God, I wish we could do labs. I have so much fun doing labs with you guys, but anyway, so yeah, and that allows you to basically repeat the process, right? So the effect here is I take current here, I put it into a magnetic field, and I've got this special split ring commutator thing going on here, which you can investigate and read about if you want to. But the effect is that this thing is just going to keep going in circles, right? It's just going to keep going in circles forever. And in the little toy cars you may have gotten as a kid, or in your, I don't know, can opener at your house if you have one of those, or any other device that has some type of rotation that occurs, even the rotating thing inside of your microwave, for example, right? The plate rotates around in a circle. All of these things are basically operated by some type of motor that at its core is literally just a magnet with a piece of wire connected to a battery or a power source like the wall or something like that. Does that make sense? This is where all, like when you plug something into the wall, when you put a battery in a device, like all of the mechanical energy that's developed, whether that be the rotation of wheels or the speed that an object picks up or something like that, it's all governed by a process at its core that's something like this. Now, this is a direct current motor. Okay, so this would be a motor powered by a battery, right? There's also something called an AC motor. It operates a little bit differently, and we'll talk about that later. But that's a DC motor. You guys have any questions? Hopefully that makes some kind of sense. I would highly recommend that you read some more about this. I don't know that I have any problems associated with this on your homework for this section, but motors will be something that we'll continue to talk about, later on. You have a question, Tom? What if? What if you do the rotating and not the battery? Well, that's a great question. Does anyone know what happens? Do you want to make a guess? charge it, the wire, the battery, maybe? Charge the battery? Is that what you said? Yeah, that's basically right. It depends on how the battery is oriented and stuff like that, but it turns out that if you rotate the wire yourself, it will actually send current flowing in the opposite direction. And that's electromagnetism, basically. There's other pieces of this that I'm leaving out. The current carrying wire here, it actually produces a magnetic field that's opposite to the existing magnetic field. And that has the effect of actually slowing down the rate of rotation. There's a balance that occurs between the input current versus the what we call back EMF. And that's going to be one of the more complicated topics that we'll talk about later. But you're absolutely right that if you just take the same system and you replace the battery, let's say with a light bulb, this is a better way to think about it. Take that battery, replace it with a light bulb, and instead of and then if you just rotate the wire inside of the magnetic fields, it will generate electricity. That's how we generate electricity. That's it. That's how we do it. We generate electricity by exactly what I just described. You rotate a loop of wire inside of a magnetic field, and it produces electricity. That's where the electricity that's powering the computer that I'm talking to you over right now is coming from, is by rotating a wire inside of a magnet. So that's a great question, Tom. Yeah. We call that a generator. There's motors that take electrical energy and convert to mechanical energy, and a generator which takes some type of energy and then converts it back into electrical energy. So yeah. Oops. All right. I don't have any problems associated with this. Like I said, this is just a concept that you should understand. That if you're going into electrical engineering, you'll learn more about this stuff. Well, any kind of engineering, really, because motors are kind of at the core of a lot of electrical applications. What did I just do? Oh, so I can get rid of the thing. That's interesting. Okay. All right. So now we move into a new chapter. This chapter is where things get really, I think, tricky. For the next couple, at least. Your book has this picture. And I don't know, I feel like showing it to you because... So we're moving on to chapter 28 now. And the opening of chapter 28 has a really good picture. I mean, I'm kind of biased, but... This picture right here. Oh, no. Come back. Here we go. Does anyone know what this is? Has anyone ever seen this before? Look at this gigantic, monstrous device, and look how small the people are. So, this immense cylinder in this photograph is a current-carrying coil, or a solenoid. We're going to learn what a solenoid is. That generates a uniform magnetic field in its interior. So this gigantic circle right here, right? Is a huge current-carrying coil, or lots of coils of wire, okay? It's huge, it's just absolutely massive. And it's designed to produce extremely strong magnetic fields. And it's part of the experiment at CERN, the European Organization for Nuclear Research. We produce gigantic magnetic fields with this device. And we use those magnetic fields to cause particles to curve inside of them. What we want to discuss in this chapter is how can such a device be magnetic? Basically, like what is it about this type of object that makes it magnetic? This thing that carries current in a circular way. Okay, I used to work on a device like this, not this one, but one very similar to this in Chicago. Same basic type of a detector, and the detector is gigantic. It's crazy how large it is. So sources of magnetic field. For this. We've got to look at kind of an equation here. I can't derive this equation. This is the equation that came from, what's the word for it? Empirical. This is an empirical equation. And it has a name that we call the Biot-Savart Law. Now, to understand anything about this, I need to tell you something about sources of magnetic fields. And historically, the way this was supposedly discovered, and I am very dubious as to whether this is true or not. Supposedly in 1820, okay, 200 years ago. 200 years ago. That's crazy. A guy named Ørsted, okay, he was sitting in his laboratory, all right, and he noticed that if he turned on a certain circuit, that it would have the effect of causing a magnetic compass needle to deflect. Okay, so he noticed that electric currents, this is the simplest way of saying, he noticed that electric currents can deflect magnetic fields, or can deflect compass needles, I should say, can deflect compass needles. So, not needs, compass needles. And what he saw was basically this. Suppose that I take a wire, and I tell you that the wire carries a current that's coming out of the page, okay? I've got current in a wire, and it comes out of the page, right? It turns out that if I take a magnet and I put it near here, like let's say that I put a magnet right here, specifically I put a compass needle, okay? And I indicate that this side over here is the northern side, right? I think I did this right. This is what's going to happen. If I put a compass on this side, the needle is going to point like this, and I'm making this side north and this side south, okay? If I put the compass needle over here, it's going to turn out that the compass needle is going to end up pointing like this. Again, compass needles tend to point in the same direction as magnetic field lines. If I put a compass needle on top, maybe you can guess what way is it going to go. Is it going to point left or right? What do you guess? What do you guys predict? Hadron Collider. Yes, that's the Large Hadron Collider. That's it. That's what this is a picture of. Well, it's a picture of the detector at the Large Hadron Collider. I think this is the Atlas detector. I could be wrong, though. What direction is it going to point on top? What do you guess? If this one points right and that one points up, what do you guess this one's going to point? Left or right? Yeah, and why did you predict left? You notice a pattern, right? And the pattern is what? Counterclockwise. It's like a circle, right? The magnetic fields produced by this wire is basically a circle. It's a perfect circle, actually. Not like what I wrote, but that is the magnetic field produced by a wire. Supposedly, this was first discovered by a guy named Ørsted, and the claim, at least according to every textbook that's out there, which means it's probably not true, is that Ørsted discovered this while giving a lecture demonstration. So he was doing a demo, and he noticed that something like this happened. And while that may be true, it just sounds false to me. Things like this often are never true. So anyway, he noticed that basically if you have a wire, it's going to produce this kind of circular magnetic field. And that's kind of where we begin. So noticing this effect and then trying to measure the size of that effect, people were led to this thing right here. And this is called the Biot-Savart Law. Named after the people that came up with it. And it's really quite complicated. There's some pieces in here we haven't seen before, so we have to define what they are. Okay, so the symbols in here that are new are mu naught. Mu naught is a constant, okay? It's a very interesting constant, actually. It's exactly equal to 4 pi times 10 to the negative 7. And I think the units are Teslas meters per amp. Yeah, that looks right. Yep. Because that's amps. This whole thing is going to have units of 1 over meter, so this will give you Teslas on the left-hand side. This is often referred to as this has a great name. It's the magnetic permeability of free space. It describes the strength in which magnetic fields can be set up in free space. You can compare it to this symbol that we've learned before, which was epsilon naught. Epsilon naught is the same version, except this is often called permittivity of free space. I don't know where they came up with these names. They both mean exactly the same thing. Permeability, permittivity, they sound like the exact same word to me. I don't know that there's any difference between the two of them, although I'm sure your English teachers might tell me differently. But permeability, permittivity, I don't know. One's magnetic and one's electric. That's what I know. And these are physical constants associated with our universe. This one's unique in the sense that it's exactly 4 pi times 10 to the negative 7. We're going to learn why that's the case later on. So that's our equation right there, right? And what this equation represents is, suppose that I take a wire, okay? And let's say that it carries some current I, right? And let's say that I want to come to some point over here that I'm going to call P. And let's say, what if I want to figure out what the magnitude of the magnetic fields at point P is equal to, direction, etc. Okay? What this states is that I come to my object here, my wire, right? And I need to have a ds. Okay, what's ds? ds is going to be a small element of the wire, like this. Okay, so ds represents a length of wire. Well, we'll just say it like this. It's an infinitesimal length of the wire. I mean, is this a line integral? There's a cross product. Like, work is a line integral. Work is equal to integral FDR, right? But that's a line integral. Potential difference, also a line integral. This one's negative Q integral EDS, right? I don't know what this is, man. It's like some kind of cross product integral. I don't know if you guys do this in... I've only ever seen this with the Biot-Savart Law, but I don't... I mean, I'm a physicist, so I live in the world of physics. It's kind of like a line integral, because we're going to break it up into a bunch of pieces, so maybe it is a line integral? I don't know, man. I'm really not sure. But the ds is an infinitesimal portion of the wire, and if you're thinking about line integrals there, you're thinking the right way. It's just we have to handle it a little differently, because we're not just doing ds and then what's r hat, right? Okay, so we need some other lines on here. So the next line that we're going to draw is a line that goes from where this object is out to the point P, okay? People sometimes get this backwards. In fact, I'm pretty sure that your textbook draws this wrong, but I could be wrong. I know that it's always kind of, oh man, this is, can I move the point real quick? I'll move the point forward just a little bit because that was going to be a right angle, and that's going to make it way too easy and also hard to see what we want to see. We'll move point P there, and then we're going to connect a line. Use black, that's fine. Oh no, it doesn't want to click. I don't understand how to use these things. What? If anybody at all knows what I'm doing wrong, please let me know, because this happens from time to time. Do I just have to like dot and then click? What if I just don't want to use that tool? Okay, pushing escape worked. That's good to know. Okay, so now from this point ds right here, a line element that carries some current I, we're going to draw a line. Black's probably not good. We need to use another color to distinguish what we're doing right here. So we'll draw a line up to the point P, okay? And that line is going to create a vector that's called R. Okay? We call that the position vector, okay? So R is a position vector drawn from whatever, the wire to the point. And then there'll be an angle that's made between those two that we'll call phi. R hat shall be a unit vector that points parallel to R, but has length 1, right? So there's R hat. And I think we have everything we need here. Now what you have to do is to figure out the direction of the magnetic field at this location, you need to do the ds cross r hat thing. That's where the direction is going to come from, right? So if you do ds cross r hat, you point your fingers of your right hand in the direction of ds, and you rotate to r hat. What direction does your thumb point? Oh, you did? Integrals like this for surface area? Okay, that makes sense, actually. That makes a lot of sense. Because you probably talk about normal vectors and stuff like that, and how the normal vector changes over the surface area. That's a very good point. I didn't think about that. Nice. That's good to know. Out, he says. That's your answer to the question, right? I'll ask the question one more time, make sure everybody understood. I want to find the direction of the magnetic field at this point right here, and what we're saying is that the direction of the magnetic field is going to be out. And that's because out is the direction associated with ds cross r, right? You do ds cross r hat, you get a magnetic field over here that points out. If you do the same thing on the opposite side, so let's say we come down to the opposite side over here, and we have some point right here, and we call it like P prime or something like that, and then we go through the motions of doing all the same stuff, right? We draw a line from here out to here. Oh, God. Why must it be so difficult? We draw a line from here down to there. That line represents the vector r. And then r hat is obviously a line that goes like that. And now you do r cross ds. We'll give you guys some time to think about this. If I do this r cross this ds here, what direction does my thumb point? Is it out or in? Oh, wait. We got the other one wrong, actually. That one's wrong. Sorry. I hope I didn't confuse you guys. Well, I'm sure I did. Sorry about that. So here's point P, right? You do r hat cross ds, and I would say that you get a vector that points into the board here. I don't know if you guys can see that. But on this side, I would say you get a vector that comes out of the board. So from on the P side here, try this. Do r hat cross ds on this side. Or just r cross ds. What direction does your thumb point? You point your fingers like this. For r, that's the r hat direction. You're going to rotate to the ds direction. So that's like your hand right there. You're going to rotate your hand like that. What direction is your thumb pointing? Do you guys understand? It's in, right? Hopefully you guys can all see that. It's really important to be able to see this kind of stuff. But if you do the same thing over here, right, you have to flip your hand around, right? Because if your fingers are pointing down like this, and you got to rotate that way, now your thumb points out of the board, right? Can you guys all see that? So it appears as if on the top of the wire, the field is in, and on the bottom of the wire, the field is out. And that'll be true for any point. You can inspect every single point if you want to, right? One thing we can learn from this, right, is let's make this really simple. Let's look at just a single wire. Suppose I have a wire that carries a current I. We just figured out that the magnetic field on the top goes like this, right? That's the magnetic field above the wire. And the magnetic fields... Oh my God, I'm crazy. Because that's just completely wrong. Wow. Wow. You guys see what I did wrong? Does anyone see? I got the directions backwards. I was doing r cross ds, but it's ds cross r. You got to go from ds to r. Whew, I am really sorry, guys. It was right the first time. We'll go through that again. We're going to go through that whole logic again. You saw it, but we weren't sure yet. We're just going to go through the logic again 100%. This is one of the hardest things in Physics 1C, for sure. And I'm making it harder for you guys. Okay, so we're doing ds cross r, right? So ds is this way. R hat is this way. And we're doing ds crossed r. So now your thumb on the top goes out. Yeah, okay, so what we had first was correct. B is out up here. And over here, B is in. Because if you rotate your fingers from ds to r, then your thumb points out on top. And if you go from ds towards r on the bottom, your thumb points in. I was just doing it backwards. So on our picture over here for the wire, on top, the magnetic field points out of the page. Draw little dots right here, thick dots. And on the other side, we've got the magnetic field going into the page. Now, one thing other about this that we can say is, according to this equation right here, it says that the magnetic field falls off the farther you get away from the wire, right? So the way I would say that is that I could draw like dots that kind of get smaller as I move away. Because the farther away that you get from this wire, the weaker the magnetic field becomes. And this is one way of visualizing that the field just gets weaker as we move away. Does that make sense? And it should, right? I mean, the farther you are from the wire, certainly the size of the field is going to get smaller and smaller as you go away. So this is how I kind of like to think about this. Now, there's another way of figuring out the direction, and it's way easier, okay? If you just point your thumb in the direction of the current, your fingers of your right hand will sweep around in the direction of the magnetic field, right? So for this one right here, take your thumb and put it on your screen pointing out, and look at the direction that your fingers rotate. They kind of sweep around in the direction of the magnetic field. Can you guys see that? You put your thumb pointing out of the page right where that eye out is, and your fingers rotate in the direction of the circular magnetic field that's produced by that wire. You can do the same thing for this wire right here and say, point the thumbs of your finger this way, so there's your thumb, and then your hands are going to be situated like this, right? And you curl your fingers of your right hand basically kind of around the wire like that, right? And that's the direction of the magnetic field. It's circular. It comes out here, and then it goes in here. Just like lacing your shoelaces or something like that. Or like a coil, right? It comes out on one side and then goes in on the other side. And it just wraps around the wire. So the magnetic field is kind of out this way, and so on and so forth. Can you guys see that? You just point your thumb along the direction of the wire that the current is flowing, and your fingers wrap in the direction of the magnetic field. I hope you guys can visualize that. It takes some time. You have to think about these things, but I hope that's something that you can figure out. You'll eventually get very good at this. We'll do a lot of problems with this stuff, a lot of conceptual problems, and you'll eventually, I think, naturally understand exactly where this how this works. Okay. So now the goal is to do an actual calculation with this Biot-Savart thing right here, and the normal one that we do first is we look at a straight wire and we define the magnetic field for a straight wire, and we just kind of build from there. So that is this problem here. These guys got separated from each other. Oh, whoops. There we go. So that's the Biot-Savart Law. Do you guys have any questions? We'll go back up real quick here. Any questions about this? All right, I wouldn't doubt if that's all very confusing. I will promise you that after we're done with some of the theory here, it's going to get really easy. And that might be hard to believe, but I promise you that it will get a little easier once we've done some of the theory here. So this is the scenario. Consider a thin straight wire carrying a constant current I and placed along the x-axis as shown in this picture here. Determine the magnitude and the direction of the magnetic field at point P due to this current. Okay? So point P is some point kind of right here in the middle, and we want to calculate the magnetic field at that point due to our wire right here. And you've got these angles theta 1 and an angle theta 2 right here. Okay? We're finding the field at that point, right? And I'm probably going to do most of my notation on this figure here. So let's stop for a second and look at what our picture looks like. So we've got a wire that goes with current from left to right, and we have a point P here that we're looking for finding what is the magnitude of the magnetic field at this location. Now, our equation states that we can find the magnetic field if we take mu naught times the current divided by 4 pi, and then we do this integral. But what we're going to do is we're not really going to do the integral immediately. We're just going to say that each piece of the wire is going to contribute this ds crossed r hat divided by r, and we're going to evaluate what this is before we do the integral. We're going to kind of set this all up before we do the integral. So we're going to go piece by piece here. The first thing we're going to look at is what ds cross r hat is going to be equal to. Okay? So our angle is defined as theta right there. And yeah. So what is ds cross r hat equal to? Not r hat. So ds cross r hat means I need to find the magnitude of the vector ds. Oh, whoops, not that. Magnitude. And I need to multiply that times the magnitude of the r hat vector. The magnitude of r hat is just 1. But then I also need to multiply by the sine of the angle made between these two objects here. And that angle would be this angle here. We'll call it phi, maybe. But then I would ask you guys, what's the sine of phi equal to? It looks like a circular interval. What's the sine of phi equal to in this picture right here? A over r, someone already said. That's right. Sine of phi is equal to a divided by r. Right? So the magnitude of ds is just going to be dx, and that's mostly because it's just pointing in the x direction, right? So this is dx. The magnitude of r hat is just 1. And the sine of phi we're saying is a over r. So I think that ds crossed r hat is just equal to dx times, we'll call it just adx divided by r. Okay? We might actually want to keep the phi in here. We'll have to see here in a second if we decide that we want that phi to show up back in our equation. Because another way we could write this is that sine of phi, I think, is also equal to the cosine of theta, right? So another way to write this would be as basically just dx times cos theta. And that may actually be the way we want it. So one of these two we'll use. It's not going to matter. It's just going to depend on which one we feel is more useful. Okay? So it's either dx cos theta or this. Now, one thing I've left out, though, is there's actually a direction associated with this, right? What's the direction of ds cross r hat? Is it out of the board or is it into the board? Out, right? So I would say this is multiplied by k hat. You guys agree? K hat. Okay, so let's see if we have enough information to plug everything in right here. So we're saying that each current element is going to produce a magnetic field that's going to be equal to mu naught times I, now these are constants, divided by 4 pi. We have to multiply that by ds crossed r. That's a 4. That looks really bad. There we go. So this is a 4. We're multiplying this by ds crossed r hat, so that's going to end up becoming dx cos theta k hat, and that's all divided by r squared. This might look kind of familiar to you guys. We did a problem almost identical to this, except it was for the electric field for a thin straight wire. And the setup was really similar. This is the only difference here, actually. So if you go back in your notes, you'll notice that we're going to do a lot of the same things. Now, in order to actually evaluate this system, right, we need to be able to get dx, theta, and r all into the same type of variable, right? Either everything needs to be in x, everything needs to be in r, or everything needs to be in theta. Yeah? And we can do that because they're all related to each other, right? For any point that I pick along the system right here, like suppose I pick this point right here, on the edge of the thing, and I gotta try. So if I label r as the distance between that point and that point right there, maybe we call that r prime or something like that, you can see that the angle theta is different as well, and you can see the distance x is also different right here, right? So all of these things vary, right? Every single one of these things vary. The theta, the dx, and the r. So we need to get everything in terms of the same variable, okay? And what I'm noticing is that the way that this is defined here is that theta 1 is on this side and theta 2 is on this side over here. So we kind of would probably just want to get this in terms of theta, I think is the idea here. So then we need to think about how x is related to theta. X is going to be the distance, so it looks like this is our origin. Then x is the distance between here and here. So then for x, we can say that x is related to theta through a, right? I think we can say something like tangent of theta should be equal to x divided by a, right? which means that x is equal to a tan theta. And our goal is to get dx, right? So dx then will be equal to a secant squared theta. And of course d theta as well. That gets our theta in for x. And then we just need to do the same thing for r. Since a is going to be a fixed length that doesn't vary in any way, we're going to say that r should be equal to, well, if we did r times the cosine of theta, it would be equal to a. Let's write it like that. If we write r cos theta, that's equal to a, which means that which means that r is equal to a over cos theta, or just a sec theta. Now we can plug everything into our equation. We're going to say that the magnitude of the magnetic field B is going to be equal to mu naught I divided by 4 pi times dx, but dx is equal to this term right here. So a secant squared theta d theta multiplied by cos theta from before. And then k hat is still there. We need to replace r. R squared is going to be a squared secant squared theta. And now we get a bunch of cancellations. Let me know if you guys are getting lost at all. So this term is going to cancel with this term. One of the a's will cancel. And so we end up getting the magnitude. Oh, whoops. This is still dB, really, isn't it? To get the magnetic field now, we're going to have to integrate. So we'll have mu naught I over 4 pi. And now we're going to be integrating. I think the only thing that's left is cos theta d theta. There's an a right here. So we have cos theta d theta. And we're going to be integrating from theta 1 up to theta 2. So we end up getting b is equal to this integral will become sine of theta, right? And I think that's the answer. We could have done this by replacing any variable we wanted to. I think this is just the simplest way to do it. Yeah. Do you guys have any questions? The dreadful lab manual is reminding you of that problem, right? It's very similar. Yeah, that's right. Now, I don't think I know that Dr. Hacking gives problems to the lab manual where you have to use this to solve. There's one in particular he really likes. And maybe I'll give it to you guys way later on, but I usually don't, because I think we've been through enough of the dreaded lab manual problems, as you say, so to speak. Now, here's the cool thing about this. Yeah, it took you an hour because you're integrating wrong. Yeah, the integration on that particular problem you're describing is really brutal. So let's look at an extension of this. So this is going to be, we're never really going to, there's like one problem I think where you're going to use this equation, but there's a more general equation we can get from this that's really good. Suppose that my wire is infinitely long, okay? Maybe not infinitely long, but suppose the point P, because there are no infinite wires, suppose the point P is extremely close to the wire, okay? And in fact, let's just say that the wire goes off the page now. So our wire just goes on forever, right? So far that we can't really see the edge of it, right? Meaning that if I were to try to come in here and figure out what my angles are, well, let's just say that they're going to be huge, right? I try to draw my angle that it's getting close to, but this ends up being, one side of my line, and now that ends up being my theta, 2, and then my theta 1 is going to come all the way from over here, and that's my theta 1 right there, okay? So what I would say is something like, if we want to make for a really long wire, or maybe for an infinitely long wire, what happens to those angles? What happens to theta 1? And what happens to theta 2? If we imagine an infinitely long wire. My picture here is horrible, but just imagine that this wire gets longer and longer, and this wire gets longer and longer. What happens to these angles? What do they approach? Does the question make sense? For an infinitely long 90 degrees, yeah, exactly. I'm going to use pi over 2. And I'm going to say that theta 1 is going to become negative pi over 2. And that theta 2 is going to become positive pi over 2. Okay? Basically defining it so that the positive angles go that way and the negative angles go this way. Okay? What does my equation become then? Oh, I left some... bad. K hat. Sorry. My equation now is going to become... I'm going to get mu naught I over 4 pi a. That's going to be the same. But inside of here, what am I going to get? Sine of... If I make theta 2 pi over 2 minus the sine of negative pi over 2. And sine of negative pi over 2 is... This is going to be negative 1. And this one is 1. So 1 minus negative 1 is 2. So the whole thing reduces down to mu naught times I divided by 4 pi a, but then you multiply by 2, so it becomes this. And then it's times k hat, but I'm just going to say this is the magnitude now. Okay. This is the one you're going to use a bunch. Now that equation is simple, right? You take mu naught, which is just a constant, divided by 2 pi. Basically, just ignore the constants. The current divided by the distance, right? Because a is the distance now. And that means that, oops, suppose that I have a long wire, right? The size of the magnetic field, okay? I'm going to take a wire and we're going to say, suppose we have a wire that carries a current that comes out of the board, okay? And the wire is very long. If I come out to some distance and we call that distance A, then the size of the magnetic field right here, first of all, the direction it points is given by the right-hand rule, and it's going to point perpendicular here. That's the size of the magnetic field, right? And it's the magnitude of this field happens to just be equal to mu naught I divided by 2 pi a. That's it. That is super simple to use. Very, very simple to use. We're running out of time, so next time what we'll probably do is say, suppose that I've got a wire that carries current I here, and we call it positive I, okay? And next to it, I put another current carrying wire, but it has a current that goes into the page, but it has the same value I. If I then come to this point in between the two of them, we could calculate what the size of the magnetic field at that point is, right? So let's define this distance here to be A. What's the direction of the magnetic field created due to I at this location? Is it up or down? The direction of the magnetic field right in between the two of them, is it up or down? We've been lecturing for a long time. I'm sure you guys are really tired. Maybe we can maybe just delay this to next time. But I'll tell you that the magnetic field here is going to point up due to that guy. And the magnetic field due to this one, it's also going to point up. Both of them are going to point in the same direction. And the field at that location would just be mu naught I over 2 pi a plus mu naught I over 2 pi a. That would be your field. Gets a little trickier when you come to a point right here or point over here, but we'll look at that next time, right? That's where we'll start. So that's probably a good point to end on. Do you guys have any questions before we stop? It was like an hour and a half of consecutive lecture, maybe more like an hour and 20 minutes. So I apologize if you guys got a little tired there. I also get very tired writing on this pad and talking to myself in my house. I'm talking to you guys, but it feels, I don't know. Do you guys have any questions?
What's the name of the law again?
Oh, the Biot-Savart Law? Yeah, the reality is that while we just made it, we just use it to derive something, right? Most of the time, this is what you're going to be using. This expression here. Or we're going to derive what the expression is for a loop of wire. And for a loop of wire, we'll find that it's like mu naught I over 2a. So that's going to be one of the things we derive next time. But it's called the Biot-Savart Law. It's an experimentally determined law. And it's how we create magnetic fields. This is where magnetic fields come from. They come from currents. Current is the thing that produces magnetic fields in the same way that electric charge is the thing that produces electric fields. So contained within this idea is the fact that magnetism is just a different aspect of electricity. Magnetism is what happens when charges move. And electric fields, or electric, whatever you want to call it, electric fields, are produced from static charges. Static charges make electric fields, moving charges create magnetic fields, but it's all the same concept, right? It comes from the same basic idea. Charged particles, positive, negative, moving, not moving. They form these things that we call magnets. And yep. I'm going to go ahead and stop the stream for now. I will upload these to YouTube.